This is John Black Superchem. We're here on part 15, polarizer fundamentals and the three polarizer paradox. Which, and look at this guy. So you can't, you can only induce jiggle vertically within an atom, because this is, when you're doing induce a current, not a jiggle. You're talking about jumping from atom to atom. Okay, here you're just talking about jiggling it inside the atom. You cannot induce anything diagonal, you know what I mean? So when you induce something, right, whether it's jiggle or current, right, you only get, like from here, you only get power from the x-axis. Here, because you can't give any of your force or whatever to the horizontal axis because you don't have enough. You either got, if you don't have enough energy to make them leave the orbit of the atom and go to the next atom, you know what I mean, and go and live there or whatever, like a current. If you don't have that, then you can't just give them part of it, you know what I mean? But you can give it to the vertical, right? So this guy's going vertical. He can't do anything in the horizontal, so all of it goes to the vertical. But you can see here the jiggle, the E field is smaller than over here, right? Because you can't jiggle it. You can't give them that much energy. It's not as much energy as over here, because this guy's jumping from atom to atom. This guy's just jiggling, okay? But you still get you get the biggest jiggle you can get by being vertical, because all of your power, all of your force, there's none in the horizontal, so all of it goes to make this B field and E field. Now, what happens in between? These are in between 0 and 90 degrees, right? Well, when you tilts down a little bit, let's say this is 1 degree off, right, from vertical. Well, you can't do it horizontal, so you do the vertical, and a little bit of your force is in the, because if you made this into a vector, right, two vectors, an E and a Y vector, right, you can see all of it's in, you'd have a vertical line of 10 feet long, and your x-axis horizontal line, it's going to be like an inch. All of it you can see. So you pretty much give all your energy to make this E field in the polarizer, right? But not as much as this, and not as much as this. So you get a little bit smaller. You get the trend here, right? Here's the one that's like at maybe 22.5%, right? Or degrees. Look at his. He got a smaller E field because he's got more in the horizontal, and you can't translate that to the vertical. You only can translate the vertical to the vertical. So anyways, this makes an E field, and then this E field makes a B field, and so on and so forth until you're down here. You're almost at 90. You're at 89 degrees difference from vertical. So all of your force can only go to the horizontal, but you don't have enough to induce, so you can't do anything there. But some of it is in the vertical, so you will you will have vertical. You will induce vertical jiggling. But you can see how small it is, and that is what makes the V field here. So you can see how small that is, right? But you can see how this is making a wave, right? It's just getting small. If we did the other side, like this is just one side of the 180 degrees. If we did the other side, it'd go back up. It'd be like a little wave, right? So you can see why these people get in more, like a big percentage of these get in. Look at the B field. It's big, giant. And then these, why they don't get in that much, like, 99% don't get in or whatever, yeah, that's because they have no B field. How are they going to react? The torque depends on these two B fields, okay? And look at them. This one's tiny, and this one's big. This one's in between. You know what I'm saying? That's why it goes down and down, right? Now look at here, okay? We got what do we got? Instead of a 0 degree, we got 1 degree, 22.5, 45, 67.5, and instead of 90 degrees, we have 89. Okay, because we gotta because if you have 0 or 90, you have no torque, right? So they don't count. So look at how the percentages go: 99, 85, 50, 15, 1. Although this should be 100 and this should be 0, right? If we were talking about vertical and horizontal. Now look, the blue on these scribble marks, only the blue gets filtered. Look on this one right here. He's at 1 degree, right? Look at the blue. Remember, we're talking about a dot here. This B field is oscillating back and forth. See the red part? That's the position. All these positions on this blue line is red. So that means they got through. Only blue gets filtered. But when the dot is here, right, the B field dot, it can't, look how far away it is. Here it's close. Over here it's far away. But since you have such a big B field here, right, all of this gets in. All this stuff here gets in, right? Any position. You can be in any of these positions and you'll still make it through the filter. But if you're in this position, the furthest away, then that's the 1%. When it goes through and to the the B field on the polarizer, right? When it hits it, right? Here's the polarizer. You don't know if the thing is going to be like this, the B field. Is it going to be far up here? Is it going to be down here? Is it going to be in the middle? Where's it at? It oscillates, right? And so your torque oscillates, so your percentages oscillate. That's just common sense, man. So you can see here 22.5. This is 1/4 of the way, right? Because this would be half, 45. 90 would be all the way, and then you start back over again. So this right here, right? Look at this. All this red part on because this blue dot is oscillating back and forth on the B field, right? All these positions from here all the way down to here make it through. But you can see 15% of there, 15% of that, it ain't getting in, right? And why? Because you made the B field here smaller. So now you got to be closer, right? So over here, you only had a little bit of blue. Here you got more blue because you have a smaller B field. So you have to be closer to get that torque, to have enough torque to turn you by the time you get through the filter. Same here, right here. Here, it's half blue and half. So that means when you're oscillating, when you're on the bottom side of this E field, right, on this thingy here, yeah, you're close enough right here. You're close, and you will get through, okay? But if you're oscillating when you're on this side of the red line, yeah, you're not close enough. Your B field is smaller now, so you need more torque. You got to be closer now, and you ain't doing it. Now over here, you got what? 85% doesn't get in. Yeah. You know why? Because you induce such a little B field that, you got to be really close. You got to be this close now. The 15% that are close, right? They're the only ones that get in because they're close enough with their B field. And what about this guy? Look at that. His B field he induced is like non-existent. So again, just like over here, this was so giant that everyone got in except the tip, the furthest tip away. Same thing over here. Everyone don't get in except the tip, the very tippest tip that's closest, because it's such a small B field. You know what I mean? The rest of them can't do it, man. Basically, they put two bunch of photons through a vertically aligned polarizer so that they were all vertically, okay? But they didn't care where the dot was on that vertical line. They're all, they didn't give a crap. Same way with the horizontal blue line, the B field. That dot could be anywhere, okay? And every photon they let in, it's different, okay? And so when it gets to here, right, you still have these same percentages. They're so, I don't understand. There's 4 fields that oscillate, and they determine everything. And yet, when they get probabilities that are percentages that oscillate, like down here, they oscillate. They're all confused. They're all like, whoa, man. Everything oscillates that dictates, everything that's going on, all these fields. But we think that it should be a uniform probability. It's like, that's insane. You are insane. But to be disingenuous saying how, this is what notice how he says this is what a quantum entangled, 2 photons is. And then he tells you how, you put them through these 2 verticals, and then you can put it through 2 more, one here and one here. And no matter what this analyzer is at, up, 1 degree, 2, 5, 7, 100 degrees, 90 degrees. You'll always get both of them going in, or both of them not go. You know, both of them coming out, or both of them coming. They're getting stuck. You know, not coming out. That's not you. Even if it was, you know, there was a thing as quantum entanglement, which there is not. Okay, but if there was, you could never prove it, because when you go at 0 degrees, 1 degrees, 2 degrees, and sure, you can get probabilities where it goes through, they both come out, you know what I mean? But sooner or later, they're going to hit 90 degrees, and they're going to get killed, right? You know what I mean? But even if you didn't have your B fields and E fields, you know, even if you didn't have them synced up, you could still have this happen where they all come out, just because you have a probability of coming out of every degree. There's a little bit, if they're all randomly whatever, a little bit from each degree goes in. 89 degrees, some of them, 50 degrees, 1 degree. But keep in mind, you can send out 2 photons, right? Put them through the same filters, you know. 1 degree, that you can put them, except for 90 degree difference between the filter it came out of and the filter it's going into. As long as you don't do a 90 degree one, you could have 2 photons that for the rest of the life of the universe, you can just keep putting them through polarizers, and both of them keep going through, keep surviving, you know what I mean? But that's not because they are, you know, quantumly entangled. It's because the B field, because each time you put the photon through a polarizer, you never know where the position of the oscillation will be when passing through the filter, right? They always make sure that they all have the same plane, right, wave plane, but they don't care where in, you know, you're going to be this oscillation. They don't care if the photon is up here, down here, you know, the B field over here, they don't give a crap. As long as they got the E field in the same plane, they don't care. It's like just like flipping a coin. You're not going to flip it exactly the same every time. Just like this, you're not going to put them in at exactly the right time so that they all hit this polarizer, you know, at their crest. You know, some are going to hit it at the trough, some are going to hit, you know what I mean? And it's not because there's you know, it's mystery or whatever, right? If you could see the B field and E field oscillate, right, then you could figure it out to when he's going to get to the polarizer. He's going to get there to the crest, the trough, and then you can know, is this guy going to get through? Yes, he's going to get through. Oh, this guy ain't going to get through. But unless you know this information, you can't never figure it out. And every time you put it through a polarizer, you reset the probabilities, because you still have an oscillating B field and an oscillating E field that you're not taking account of. The B field, when you know, that's what determines it, and it oscillates, so your probabilities oscillate. Even at 89 degrees, you still have a chance of getting through. And every time, just like when you flip a quarter, it gets reset, right? So it's 50%, you have a 50-50 chance every time you flip. It doesn't matter if you have 1,000 flips right before that were tails. You still have a 50-50 chance. It's the same with this. Because we never do anything about the B field and the E field, about where they're at. They only care about getting them all in the same plane, but they don't care about where they're at in that plane. You know, their oscillations. Let's say you just infinitively put that photon through an 89 degree, you know, differential with the degrees. So he has very little chance to get in, but he still has a little bit of chance, because he still has it. You can see right here, he still created a B field, right? So he still has torque. As long as his B field oscillation is close enough, like down here instead of up here, it will get through. So your probabilities get reset each time you do the experiment. So these people act like they don't know that. Okay, they act like when you flip a coin, leprechauns in the background. Oh, he got a heads. Oh, he's got a tails. Oh, he's got a heads. And someone keeps track of it to make sure that you get 50-50. No, it's just the coin is has enough evenly mass on both sides. That's all it is. Same way here. It's just that you oscillate your B field So you're oscillating the torque. So you are oscillating the probability